everybody, 2-minute warning. Please grab a seat and grab a beer or whatever food you may need, and then sit down because we're going to get started. Thank you. All right. Whoa. Oh, hey. How's it going? Y'all ready to start? So, hello, everybody. My name's Alan. Welcome to PuPPy's monthly meetup. We do this the second Wednesday of every month of the year. Sometimes we change the date, but 99% of the time it's the second Wednesday of every month. How many of you are here for the first time for a PuPPy meetup? Wow. Okay. Welcome. Thank you for coming out. For those of you who are not familiar with the format, we typically start with, I dropped something. We typically start with lightning talks, then we go into regular talks, at least one, and then we have a short break, and then we have a final talk, and then we go to an after party. The after party this month is at Feuer's. It's just right around the corner. Feel free to follow me or anyone else who knows where Feuer's is at the end of the venue, at the end of the meeting. If you don't know where it's at, you want to go, find someone who knows. If not, just follow me. I'll lead you the way. So, without further ado, tonight's sponsor is Indeed. A quick round of applause for Indeed. Thank you for hosting us. They were nice enough for you to sponsor us with a venue, which is pretty kick-ass, if you will, and a bunch of great food. So, thank you. George, you want to talk a little bit about Indeed? Maybe if you guys are hiring or anything. Maybe you are, I don't know.
Yeah. You know where you can find a job. Yeah, you might have noticed our recruiters' business cards on the food bar out there. My name is George Murray. Our site director, Ken Parker, is out of the office today for a family emergency, so he's not around. Feel free to come to me or anybody else with questions about Indeed. So just a quick spiel. Indeed is by many accounts the #1 job search site in America / the world, depending on who you ask. We deal with quite a bit of data day in and day out. Anybody who works for Indeed in the room, please raise your hand. All right. So there's a bunch of people with I help people get jobs, and there's also anybody with their hands up. Our first talk tonight will be a lightning talk by one of our data scientists, Benjamin Link. He'll tell you a little bit about how we use Python at Indeed. Also, our main production stack is Java and Spring MVC. Let any of us know if you have any questions about what we do today. We're a very data-driven company. We've been around about 10 years. And yeah, enjoyed the meetup.
Ben's going to start us off. He's got a nice lightning talk. I forget what it's about already. I apologize. It involves Flask. He is a data scientist at Indeed, so I'll let him take care of the rest. I have a microphone, so when you want to ask a question, raise your hand, and I will run at you as fast as I can with a microphone, so everyone can hear your question. What's up, guys? This is awful.
Someone have one? Try unplugging it. Ben, unplug it and plug it back in.
Solid strategy for everything.
And then reboot. It sends the wrong signal over time.
Boom! That's going to be better than the entire talk.
Do you work IT?
Product guys.
Oh,
sometimes between presentations.
I see, all right.
Fighting with projectors.
All right, so my goal in this talk is to walk you guys through building a machine learning model and then deploy it in a Flask app and do it in 10 minutes. All right, so there's a common data set in data science. It's called the iris data set. It essentially involves flowers. And I will show you a nice little picture of this data set. And there's four measurements talking about like the width of a flower petal, the length. You can see kind of an example here. There are three different types of flowers that are in this data set. That's Setosa, Versicolor, and Virginica. And in this case, you can see some nice plots that show how these kind of groups are very separable. So this is a really good case for building a model because we are pretty confident that we can separate these three different colors. So in scikit-learn, this data set's really easily available. We can load it by essentially calling this nice function here called load iris. And we can see what the features are for our data. And in this case, we see measurements for different parts of the flower. We can also see what the different classes are in this data set. And then we can build like a nice little matrix of our data. In machine learning, really everything boils down to putting something into a matrix so that we can predict things or we can analyze things. So in this case, we have an X matrix and a Y matrix. The X is the data that's going to help us predict something. The Y is the labeled for these pieces of data. So Setosa, Versicolor, or Virginica. I'm going to use a random forest classifier, and I'm going to do something called cross-validation, which essentially is I'm going to build a bunch of different models on a bunch of different parameters and kind of pick the best set of these parameters based on how good of a job I predict things. So I'm going to get some training data and some test data. This is essentially saying take our data, split it into chunks. Let's grab some so we can look at how good of a job we're doing at generalizing to data we haven't seen before. And that's what we call test data. And the training data we're going to use to actually build a model to help us make a decision on what's a good fit. And in scikit-learn, to train a model, we just hit fit, and then it trains a bunch of models here. Wow, that's fast. It took 1.2 seconds. Very small data set. So then we get some results here. We can actually look at how good of a job we do at predicting things. And so in this case, we can see that in our training data, we predict really accurately, about 99% of the time we're correct. And in our test data, which is data we've never seen before, we've never used our model on before, we still predict about 94% accuracy. Because it looks like we do kind of bad in the last two classes, but not too bad. So I built a model, I'm pretty happy about it, let's say, now I want to actually load it into a Flask app. So when I see I have new measurements for flowers, I can actually score them on a website. So let's dump the model. And so I'm going to run this command here, which is just going to write out the model to a file. Joblib is a nice library to do things like this, especially for things that have a backend that's like NumPy based. So I'm just going to make a bunch of files. Wow. And I'm going to evaluate that I can still load this back in, and that I can still run predictions on it and get results that make sense to me. So, cool, that looks good. All right, so we have a model now. We wrote it out to a file. How can we load it in Flask, and how can we make decisions on this on a website? So here's our really large Flask app. And what you see here, I mean, all Flask app sources are on the big. So what you see here is we don't really have very much. We kind of have a nice route to a classify flower post method. It's going to essentially just take all the models we have loaded in a certain directory, and in this case we just have one. And it's going to load all the models into our app context, and then it's going to go through each of them and essentially score them. And so kind of around this, we have just some very simple code to do each of these things. So in this case, this is like making the strings to actually print the results out. This is just loading the model in. So one really nice part about joblib is when you dump a file into a Python object, you can read it back in by calling load, and it's your Python object just persists essentially. And in this case, I don't even have to have the import statements. I don't even have to have the scikit-learn import statements to load this back in and just get it for free. So that's our whole app. I'm going to kick it off. I'm actually going to kill it and then kick it off. So we load the new model I just made. And I'm going to head over to our little web app page here. I'm going to refresh it so you guys don't think I'm cheating. And I'm going to grab the same training data we just used. And I'm going to hit classify, and I'm going to get results back. And you can see that these are the 3 different classes and the probabilities of each of those. And hopefully they're the same as the one that I had that I output from the file. They are. And that's it. That's putting a scikit-learn model into a production environment, being able to make classifications on it kind of at runtime with new data, and doing it really quickly, the very minimal application in Flask. So at Indeed, we use scikit-learn to build almost all of our models for machine learning. We wrap them in lots of different layers. We make automatic emails get sent to us when we finish building a model. If it runs in the middle of the night, we run it on AWS. We can take advantage of these big, nice, beefy machines that we don't have in the office. And then we deploy them. And I think George mentioned this, like we have a Java stack at Indeed. So it's not as nice as this. We don't have a Flask app running that loads all of our models. We have a Java layer that loads all of our models. And so we actually, in reality, have like an intermediate kind of way that we write out models, similar to PMML, which is kind of a public way of writing out model types. Most of our models are decision tree based. And so I just want to show one last example here of how we kind of do this. And so we do something very similar, but we do it in Java after we unload these models. And so this is looking at jobs and kind of different predictions for a specific job that we have in our production environment. As you can see here, like we try to predict the education level for a job. So we have high school, college, or license, and then we look at experience, and we have a new education model that we just released. We have time and kind of supervising, is it supervisor role or not? And so we use all this data to help us make decisions about what kind of jobs we want to put in front of job seekers. And we use this to help us determine how good is the quality of an application. And we use a lot of machine learning at Indeed, and we're always hiring data scientists and Python experts. And so if you guys are interested, let us know. That's it.
So you're an all Java stack. Why do you use scikit-learn to generate the models?
Yeah, so it's a great question. When I started building models at Indeed, I guess it was like 2.5 years ago, we had to make a choice essentially of like what framework we want to follow. And scikit-learn's an open source framework, and it's really nice. And there are Java frameworks as well. There's Weka, there's Mahout on Hadoop. But for most of the data sets that we typically use, data expires very quickly. And so our data is not this gigantic number a lot of times. It's something like kind of reasonable size. And I want to take advantage of nonlinear models and a really strong open source community. And so scikit-learn fit that a lot better. We certainly did spend a lot more time finding ways to deal with 2 programming languages instead of just dealing with 1. But that's something that we sacrifice for the advantages of scikit-learn.
Other questions? Raise your hand. Going. Gone.
Thank you. Thank you.
So next up is George and Adam. They work at Metabrite. They're both developers there, and they're going to be talking about managing
building Docker images with salt stacks.
All right.
Certainly like trying to wrap data as an internal.
Yeah. Don't truly that.
Yeah, it's
Spring.
yeah, so like there wasn't a choice.
Well, that's AV for you.
And so,
It's always not well.
as you nowadays, we kind of like that push you
We'll be with you in half an hour on something that's great. It's about the AV stuff.
Yeah, right. Well, right. Yeah, exactly.
So Java is much slower than C.
Right, yeah, exactly.
No, I think
What are
in general,
calendars?
you have a microphone, you want a microphone. Internal tools are kind of the first step.
Right, right. Yeah.
To moving to external.
Hi, I'm George. He's Adam.
Thanks.
And we're from Metabrite. Before I start, has anybody here used Docker? Some experience with Docker?
Right.
Okay, so maybe a third. What about Salt Stack? Very few.
What about any kind of configuration management system like Chef or Puppet or something like that? Ansible, yes, Ansible. Exactly. Great. So some people don't have experience with that.
Okay, so we'll get more into a little more into what Docker and Salt are later, but very briefly, Docker is sort of a lightweight virtualization technology that's become very popular. You must have heard the name, even if you're not quite sure what it means, over the last couple of years. Basically, you build a Docker image and you run it in a container which is hosted on Linux, and it's much more efficient resource sharing, image startup and things like that. And Salt Stack is used for configuration.
It's a robot system administrator, you can think of it. It can manage lots of it can manage lots of servers and set your servers up for you if you want. So
Right. We're going to talk about a tool that we built called Flying Cloud. We built it to solve a problem, like most software has a genesis in a problem. Our problem was that we had an app that was basically impossible to actually build and deploy. It's called Nectar. It's a web service that we upload. Is the sound cutting out? We upload images to it. We run them through OCR. We extract structured data from them about the images are of receipts, shopping receipts and things. We extract structured data from them. And the OCR stack that we were using, Tesseract, OpenCV, scikit-learn, SciPy, NumPy, and probably about 10 other horrible, nasty to build things are in the mix. And we were deploying this natively on Amazon's Elastic Beanstalk service. So a Python app, but it was running on Amazon Linux, and we basically could not get it to build on Amazon Linux. It was a nightmare of dependencies and things that wouldn't compile. And we eventually abandoned the effort to build it natively on Amazon Linux, and we used the other way of deploying on Elastic Beanstalk, which is as a Docker container. And that worked, but it had its own problems. We started deploying on Ubuntu, and if the image built and deployed, everything was fine. The problem was actually building. We had this horrible nightmare of shell scripts. Is that the next image? We don't expect you to read this. But this is just some of the complicated, unmaintainable mess of bash scripts that we had.
and this is something that we found, at least with Docker files, when you're deploying Python, especially complex Python applications with a lot of libraries of different kinds, you have to do things that quickly get out of they're beyond the capabilities of, they stretch the capabilities of using a Docker file. So you have to build scripts and software, and that's what it ends up looking like if you're not careful, which we weren't. So,
Sorry, the back.
oh, yes. You want to do this one?
Oh yeah, the other problem with it was that it took about an hour to build, and if anything caused it to fail, a network connectivity problem or one of the tests failed or whatever, you had to roll the clock all the way back to zero and start over again. So that was pretty painful. So this is sort of the version 2 thing that we came up with in the last few months. That we developed Flying Cloud for. On the left, you see the old build. It's just a monolithic Docker image. It's built with one huge tangle of bash scripts. On the right, you see what we came up with. There's sort of a lower piece and an upper piece. The lower piece is what we call the daily build. There's 3 layers in there. Sysbase is just the operating system. It's Ubuntu. We're actually using a derivative of Ubuntu called Fusion, which is sort of an opinionated fork of Ubuntu that has a bunch of Docker stuff in it. PyBase is the next layer. That is Python 2.7.11 because we wanted a modern Python 2.7 because we were using Ubuntu 14.04, which is stuck at Python 2.7.6. The next layer is the one that causes all the grief, Tesseract and OpenCV and lots of other things that are just nasty to build on Amazon Linux. We have pretty much nailed it on Ubuntu, so that part always works unless there's network connectivity problems. Anyway, we build this once a day. It takes, I don't know, 45 minutes, something like that. Builds at 3 a.m. and that means we have all the latest security patches and whatever for Ubuntu. Then the upper half gets triggered every time there's a merge at GitHub. It builds the actual app. That's our, the Lectern app is our actual code, plus some bits and pieces in there for logging and so on. And then Test Runner is not additional state that's added to the Docker image. It's actually a sort of a runnable layer. We run our tests there, and this is something we found very useful. When we build the Docker container, we run the tests, both our unit tests and acceptance tests, inside the Docker container itself. So that means on our build system, we don't have to have a virtual environment that's running natively in the build machine. We just have a tiny little virtual environment that just has enough to run Flying Cloud, and inside the Docker container, we have the full stack. It's very, it's essentially the same as the code that we're deploying. It is the same code, it's just, connected to the outside world in a slightly different way. So we run our unit tests in there. They pass. We run our acceptance tests against the service that's running on localhost. So we're making HTTP calls to localhost inside the container. That all works. Then we deploy the newly built image out to our dev server. And on our build system, we call into the locally running container and make remote calls to the newly deployed container on our dev server and run our acceptance tests against that. So,
and this has the advantage basically of you testing the actual artifact that's going to production. You're not testing your code running in something else, some other environment. And when you have a fairly complicated system, it has saved us a lot of grief basically from being able to test those artifacts. So there's one big idea in this presentation. It's use a configuration management system to build your Docker images. That's really kind of a cutting edge thing to do, I would say, but that's what the approach that we're promoting. It enables us to build these very little layers that are very friendly to being reused and friendly to continuous integration. And we can configure the layers rather than writing scripts and debugging them. The reason is because SaltStack basically does everything for us. And all you have to do is configure it to do any of your system administration tasks instead of reinventing the wheel yourself, basically. So I'll say a little bit about what is Docker. George mentioned a little bit before. You can think of it basically as a virtual machine, but it shares the Linux kernel. And so what you have is you can build these artifacts, essentially, that have an entire Linux distribution in them. And that's very interesting because you can use whatever Linux flavor you need to run your application that's more friendly to whatever you're doing. If you're running software that's friendly on CentOS or on Alpine Linux or on Ubuntu, you can pick that and you're not locked in. And they can you can run different containers on a single server, and they're all separate from each other, and they're each running their own OS, and so it makes it very easy to build these custom artifacts that are really customized to your own needs instead of being stuck with a cloud vendor's particular operating system. There's two concepts that I want to talk about that are relative to Docker. One is the image, which you can think of as a file system snapshot. And that's what Flying Cloud is building, or Docker files. If you use Docker files, that's what they build. They give you an image that you can then run. And the running thing, the thing that's running when you're on a server, is called a container. It's a little, the terminology is a little generic and confusing, but that's kind of what's going on with Docker. Oops, sorry. Let's see here. And then so SaltStack, like I said, it's a robot system administrator, and there's a sort of a field called configuration management, and Chef and Ansible and Puppet and Salt are all part of that area basically. And all those systems, they have really two modes of operation. One is where you have 100 or 1,000 servers out in the cloud somewhere or in your network, and you want to administer them. And SaltStack can administer running servers. It can tell you their state, do things to them, change them if you need to, reboot them or collect information. And that's not what we're doing. The other mode that Salt has, and the other configuration management systems have too, it's called masterless. And it allows you to basically take a set of configuration and apply it to a server. And so we do that at build time. When we're building these images, what we do is we have Salt make the changes to the Docker image itself. Salt's implemented in Python, which is one of the reasons we're really friendly to it. You can extend it, write your own Salt plugins if you need to, but generally you don't. Generally, there's pretty much anything you want to do, whether it's Node.js or Ruby on Rails or any kind of system administration you can think of, installing operating system packages, moving things around the file system. Salt can do that. And so you can usually just write a configuration file, typically in YAML. Yeah, so that's Salt. And so the two ways that Docker, supported ways of building Docker images, one's using a Docker file, and you saw kind of the scripts that we were using with a Docker file. If you want to install Python and Python libraries, you quickly get into some fairly complicated gyrations with Docker files. It's really great for doing simple things like installing operating system packages that are in a package library, or changing a few files here and there. But if you get into something complicated, it gets difficult. But the good thing about Docker files is they're repeatable and automatable, right? You can just say, give me a new image, and it can do it. The other way that Docker gives you is called run and commit. You can manually log into a running container and say, hey, build me an image. And but the problem with that is you end up with these things that we call snowflakes. They're all unique. A human had to change them. We don't want that, because we want our services, our Python services, to be built by a robot. We want to be able to repeatably build the same artifact over and over again out of our version control system. So neither one of these systems was really working for us, and that's why we built Flying Cloud. And Flying Cloud, as we said, it uses SaltStack, it's masterless mode, to configure a layer, basically. And it's very easy to run in continuous integration. It's repeatable, and it gets us writing our software and gets us out of debugging DevOps nightmares, basically. So we're going to be going over an example app. It's very similar to the one that we showed, Lectern. It basically has a few base layers. The base operating system that has Salt, a version of Python, as we showed, how to basically get the version of Python that you want installed on the layer, and then some complex libraries. OpenCV is a kind of a strange thing to install, and so we have an example of how to do that, and then a Flask app and running the tests.
Okay. I want to say a little more about this.
Yeah.
So you can see that we have 3 layers in the lower part that corresponds to the daily build I mentioned earlier, sysbase and pybase. Now, if you wanted to install some completely different stack of stuff on top of pybase, you would just take those lower 2 layers in a different app and you'd build your other, perhaps hard to install pieces on top of that in a third layer. So, you know, these pieces are reusable and stackable on top of each other.
And that's why we're really concentrating on each layer as a very small set of configuration. And we'll take questions at the end. Is that okay? Sure. Okay. So you want to?
Yeah. We'll actually show you some code and the app running in a minute. But the app that we've built is a very simple Flask app. Seems to be tonight's theme. Simple Flask apps. However, our one, uses OpenCV to take an image and to run the canny edge detection algorithm on it. So it, just draws various lines around the screen. We'll show that in a minute. So there's this is just showing you a sort of a schematic diagram of how the various pieces are laid out. The panel on the left is the project YAML config file, and it's pretty much self-explanatory. The app name is Flask example, and then we have 5 layers, and each one of those layers, test runner and Pybase and so on, is a directory name. Then we've shown the first 3 layers, the lowest 3 layers on the right. The lowest one, sysbase, is a Docker file. You can still use Docker files with Flying Cloud if you want, and a layer.yaml that just has a couple of declarations about what this thing is. Pybase is the next layer up. It has every layer has a layer.yaml file, and there's basically 2 lines in the Pybase one. One just as a help string, just so you know what it is, and the other one says parent sysbase, which is just so that we have sort of a linked list of dependencies going back down to the root one. Sysbase, of course, has no parent. There's another file in there, top.sls, that's a salt state, and it declares that it has one dependency, which is the Python 2.7 update, and that jumps through various hoops to get an Ubuntu PPA to install Python 2.7.11 on top of Ubuntu 14.04. The third layer, OpenCV, again has a layer.yaml, which is structurally the same as the previous one. Another top SLS, and this one has a couple of other SLS files. One is Python requirements, which pulls in things. Well, we'll look at it in a minute, but between the two, it sets up OpenCV with the Python bindings on top of the Pybase layer.
And it pip installs all your modules for you, which, that can get complicated in a Docker file. So.
Okay, this is the main layer that, of course, of the app. This is the one that's called app. The app layer, there's a layer YAML and a top SLS as before. The layer YAML has one new field in here, which is exposed ports. All that's saying is, on the right-hand side, inside the container on port 80, our app is running. Outside the container, you can reach it through localhost on port 8080.
If you run the Docker container locally.
Yeah, and we'll bring that up in a second. The top SLS has 3 components. Nginx, we're using the Nginx web server to front all of this because it's a production quality web server, and good for serving static files and terminating SSL and a pile of other things that you don't necessarily want to do in your Flask app directly. Ubuntu packages just install some other things that we want in a production server, like rsyslogd and a couple of other things. And then Flask example, of course, the application code itself. There's another folder in there, app, and that's where the actual Python code for the entire app is. And let's see the test runner layer. And finally, test runner layer. This is not a buildable layer. It doesn't build any more state into a Docker image. It just runs a Docker image, and it specifically runs tests, like I described earlier about running unit tests and acceptance tests inside the container. That's what this does. And it is doing it in a new file called layer.py. So you can write a custom handler for your build layer. We for the other layers, we just create objects on the fly that manage all the dependencies. But if you want to, you can have a custom runner or a custom build command.
And that provides an organized way to escape into Python if you need to do something, really complicated that and this will run in the context of inside the build or inside the Docker container itself. Okay.
Yeah, let's bring up the app.
So here you go.
Okay, let's actually run the app for a second in the browser.
Okay, so here we go. Let's see. So we have a Docker container running, and there you go. I don't know if you want to talk
Okay,
about it.
yeah, briefly. So on the left is a JPEG embedded into the app. The name Flying Cloud, by the way, comes from a famous clipper ship from the 19th century. It was some incredibly fast sailing ship. This isn't an actual picture of it, it's just a Creative Commons picture of some other sailing ship. The picture on the right, however, is dynamically generated by the app of using the Canny algorithm to detect the edges in the source image. So let's take a quick look at some of the code.
Yeah. You want to drive or you want to
Right.
drive? Just want to do.
Well, this is our top level project file, the flyingcloud.yaml. As I described before, it has various layers and an app name. And also this registry stuff, if you want to push or pull your Docker images to a Docker repository like Docker Hub or key.io, which is what we're using, then this allows you to set additional config around that. For the purpose of our example app, where we just do everything locally.
Okay. What's next? Is this base?
Yeah.
Okay.
Oh, let's actually run the command line.
Oh, you mean the tests, right?
Well, I actually just run the -h.
Okay, so here we go. All right. So let's see. I'm scroll a little bit.
Yeah, we've made the font so big that it.
Here, do you want me to make it smaller?
No.
Okay.
So this is the Flying Cloud command line tool. It has various options. The first ones aren't very interesting. Scroll down a little more. Yeah. So there's three operations. By default, you just want to build a layer, and you don't need to specify anything there. And here's the 5 layers that are discovered from the flyingcloud.yaml file.
Okay, what do you want to do now?
Let's run the test, run the test. So this is actually going to run the unit tests inside the container.
Okay. So you're seeing you're seeing a bunch of logging information and then unit test output, basically, right? So
The unit tests aren't very exciting, but it did actually execute inside the thing, and that it's just a classic unit test. It's just exercising a function.
okay.
And then the acceptance tests that we can also run through here
Here.
actually make it, by default, just run inside the container and make it an HTTP call to localhost inside the container. And
So that ran.
that ran. Now, we're going to pass in a new base URL. Instead of being localhost 8080, we're going to pass in google.com. And this should fail with 404 not found. Assuming we have a network that may time out.
Yeah, we're on the internet, so I don't know what's going on.
Okay, I think we probably have a network connectivity problem. Anyway, we'll come back to this in a minute, and it should have timed out.
Yep, there you go. So what's going on is it's saying, there's a fail and there's a trace back, basically.
So obviously on your build system, you can, Bamboo or Jenkins or whatever, you can script these kind of things, running your tests inside your container, inside of some complex environment that is very, very close to what you're actually deploying in production.
Do you want to go to the code here?
Yeah. I'm not going to dive into all of these layers, but here's PyBase, for example.
Maybe show one of the SLS files.
Yeah.
Here, I'll drive.
Okay.
Just tell me what to do.
So open PyBase. Take a look at the top SLS.
Okay. Wow, that's complicated, huh?
Yeah. And now look at Python 27 update.SLS.
Also not very.
Well,
not
no,
very
there's
exciting.
more lines up above.
Yeah, I mean, what it's doing basically is just it's installing, some things that allow it to install a PPA, then installs a special PPA for Python, recent Pythons, and then it just installs the some other these operating system packages from that private repo.
Right, and it sets up pip and virtual env, and it creates a virtual env at /venv. So let's take a look at that.
Okay, so the top SLS, you want to see that?
Yeah, we won't dive into all of these, but as I said before, this is 3 things. Nginx, Ubuntu packages, and Flask example. Let's take a look at Nginx. Okay, this is pulling down a modern version of Nginx because we don't want to run the... For our real thing, we needed to do something with WebSockets or something like that, and the 2-year-old version of Nginx that came with Ubuntu 14.04 didn't support WebSockets well, so we pulled it down.
But you can see it's not a script, it's just a config file, and it just has a couple little entries in it. That's all there is. What do you want to go to next? Ubuntu packages?
Yeah, that one's not very exciting. Let's take a look at the Flask example.
Oh yeah.
So this is actually our app itself, and this just sets up the app inside the virtual environment and copies things over. And you can see that we're using pip to install from a requirements .txt file inside of the app. Let's walk into the app for a minute.
Okay. So like
yeah, an open app.py.
Okay.
So this is the route at line 29 /canny. This is the actual bit of code that generates the image on the right using the canny algorithm. We don't really expect you to follow that in detail because we don't know how it works either. Tests.
But in our app, the Lectern app that we talked about, we do have a very complicated image processing pipeline that does machine vision and does a lot of image processing steps and uses a lot of these same things similar to Candy, the image processing steps, and that's what drove us to do this.
Right, and here's our acceptance tests, which was just hitting localhost or some configurable thing that came in through an environment variable, which got passed down through the test runner code. Let's take a quick look at the test runner because that's the other interesting one.
Okay, so
It's
you're
off
looking
the bottom of the
in
screen.
the layers here, this thing.
Yeah.
You want to look at layer.py.
Yeah.
Okay.
So this is the one piece of custom Python in this application, at least Flying Cloud custom Python. We have this class which just is derived from Docker build layer, and we've implemented the do run method, which is running unit tests or acceptance tests and executing the code inside of the container. And we just effectively are using Docker run the Docker PI exec thing to execute a command inside of the container and capture the output. And yeah, that works pretty well.
Okay, so that's a little tour of how that example app works. Let's see, are we going back? Yeah?
Yeah.
Okay. So let's see. All right. So just to kind of summarize what we're talking about is we use a configuration management system, SALT, to build layered Docker images. And a Flying Cloud layer, it can be built up of a Docker file, which you can use Docker files, salt states, or you can write custom Python code, little snippets of custom Python code that will run inside this framework that manages all the naming of the layer, pushing to the repos, the registries, and things like that for you. And layers are either buildable or runnable, or both. And Flying Cloud manages naming the repos with names that are we call them strong names, so that the artifacts, when you're running an artifact in one of in the cloud, for instance, when you're deploying it, you know exactly which artifact you're using, and Flying Cloud handles that for you. We mentioned that we were going to talk about Kubernetes, but we ran out of time just to talk about this. What really drove us to build a bunch of Docker layers and Docker services, we're a Python shop, but we have multiple services. And we use Kubernetes internally, which is a cloud orchestration system. It's similar to Docker Swarm or Mesos, if you know what those are. And they manage clouds of servers as software. So you can basically have a configuration, a script or a set of configuration files that boots up a whole cluster of maybe 100 servers and can tear it down for you too. And as you can imagine, these things consume Docker containers that are really hungry for Docker images. Like every service inside it, you might have 3 or 5 or 10 different things running inside your cluster. They're all going to be on Docker. And that's just kind of the way the world is right now. You need to build Docker images if you want to get your Python service or whatever service you're building. If you want to get it out to people, it's going to be inside a Docker container. And the thing is, we didn't want to just spend all our time building Docker containers, so we just want to configure, write a few lines of configuration and get it out there, and that's what drove us to do this. So maybe at some point in the future we'll come back and talk a little bit about what we do with Kubernetes, but not tonight because we're out of time. Flying Cloud is open source, so has an Apache license, Apache 2.0. You can go to the GitHub repo and download it and use it. It's early, but we use it in production, so we consider it production quality code. If you use Salt, I saw some people raise their hands. We'd love to have you use Salt and Docker. This is like a good combo. We'd love to have your input. And if you use Ansible, we think getting Ansible in here also would be very interesting. And so if you're interested in doing that, we'd love to talk to you and get contributions or help in some way. And yeah, just try it out and run the demo if you can. It's a pretty interesting system. So that's pretty much the end of our talk. We have a Google group about that you can join, and we can do we can do support if you have questions afterwards. And of course, the last thing I'd like to say is, of course, we're hiring also. We're a Python shop on our back end. We are looking for Android and iOS devs and data scientists. So if any of this stuff sounds interesting, if you're interested in building Python services at scale, and you want to, this is what's interesting, please come talk to us afterwards.
If you have questions, raise your hand. Oh, all right. You're closer. I'm going to go to you first.
Just a quick question.
Yeah.
I might have missed this context. I'm unclear if you're using Salt inside the image. So when I start the image, when I create a new container, does Salt execute at that point? Or are you using it in the image preparation?
Yeah, it's only at build time. There is a Salt, Salt is installed on the base image, but it doesn't, it's not, there's no Salt minion running there. It only runs during build time. Does that make sense?
Yeah, so in other words, when you start a new container from the image, it's already pre-configured.
It's already pre-configured. So we're only using Salt in masterless mode to actually do the building of the container, not to contact it. You can, of course, have Salt, configure it to use Salt in your system later also. You could do it, you can do that. But the main purpose of Salt for us is to configure the image.
Okay, thanks.
All right, hands up for other questions.
Wait, anybody who
There you go.
asks a question we like.
Here we go.
So,
I'm coming. Here we go.
Yeah,
Go.
I noticed in the example code you were showing that you build virtual nodes, and I'm thinking, why? You're in a Docker image, there's no one else in there, so.
Yeah, we thought that too, but the interesting thing about there is this thing about system Python, right? And if you want to use something that's slightly different, a lot of the internal mechanisms of Ubuntu use Python, and they expect that Python to be in a certain place, in a certain version, and everything. And so if you want to upgrade it, you have to do a lot of fiddling around. And the easiest thing that we found was let the system use its Python, let us use our own Python, and we won't fight.
Yeah,
Because we're installing a lot of crazy stuff into that Python environment, and installing it into the system Python got a little funny.
I don't remember the details, but I do remember that we decided this should work, but it isn't. Let's just go with a virtual layer. It does work that way.
I'll take that mug if no one else is taking it. Other questions?
Any other questions? Yeah, there's a few there.
Right there? Right there. Keep your hand up. Keep your hand up. There you go. All right, you? All right, great. And then the other guy with the glasses, you're next. Oh boy, I gotta really chill. Ready? Ready?
So I noticed during when you're building images, you were building the Python app and then also building setting up Nginx inside the container or inside the image. What was the kind of thought process of doing that as opposed to running an Nginx container, like a Flash container, and then setting it up to kind of like linking the images?
You can definitely do that. I mean, this is a demo app, right? So we wanted to show a bunch of the features of Flying Cloud here. You know, I mean, you can definitely run a separate USB server and a separate Nginx server and connect them. But then we would have to demo sort of a cloud orchestration system, and that cut into our time budget essentially for this talk. So.
There was someone else. All right, great, awesome, thank you.
I was just wondering, you mentioned other deployment systems like Puppet, Ansible. What made you choose SaltStack?
Well, for us it came down to Ansible or Salt, and because we're a Python shop and we want to be able to extend, we didn't know whether we'd run into, we'd get painted into a corner, and we wanted to be able to extend whatever configuration management system we were using. And Ansible and Salt for us are both excellent systems. Salt just had it seemed like it had more flexibility, it had more states available to it that did more, it did more of the things that we wanted to do. But it was a very close decision for us. So I can't really, just felt that Salt felt better when we were playing around with it.
All right, Pat, all right.
I know it's not very satisfying, but you know.
I'm coming, Pat. I'm coming. You just have to wait. Stop being so impatient. All right, Pat.
All right. So to kind of follow up with that one, have there been any cases where you did need to extend upon Salt?
So far, not. I mean, once we, you know, yeah. I mean, it does. It has a vast library of system administration stuff, and so far we haven't had to extend it.
We haven't had to write Python code. We have had to write some fairly gnarly YAML SLS states, but we haven't actually had to write custom Python code for Salt.
Other hands? I'm looking. Nobody?
Wait,
whoa! Oh, I'm so sorry. I'm coming. Here we go. I'm close. Do you have any more mugs? That's a great idea, by the way.
Come up and get them afterwards.
Hi, just to get clear, when you build the layers, if you fail at a particular layer, do you save the image up as you complete each layer so that you can go back to the last good layer and build forward, or do you still have to roll back and rebuild from the base up?
No, I mean okay. So that's the advantage of doing this doing it this way especially in a CI system. We do fail hard when a layer fails. We don't want a partially working layer. That would be very bad. But all the layers below, there's still artifacts that are pushed to our repos, right? So you don't have to you don't have to rebuild. You don't have to go through the laborious steps to rebuild those. Definitely not.
Ooh, another question. I'm coming.
You might just talk a little bit about the, I guess, testing and deployment process.
Everyone can hear your question. Oh my God! Sorry.
So I was curious about the testing and deployment of once you build these containers, how do you test them with API tests or integration tests for other artifacts, and how do you deploy that to AWS?
Yeah. So a couple things. So first of all, there's a workflow that's happening here, and that's one of the things we didn't really touch on. But this system, Flying Cloud, is really designed to have a same workflow. So you basically, what you do is you there's a development phase where you're basically building the container and you configure it, and you run it locally, and Flying Cloud will help you run it. So you can sort of run either manual or automated tests against the local Docker container. You can even log into the running Docker container if you need to and look around. And once you have that, and then you've checked it in, you merge it, and your CI system, our CI system will build it in CI, push it to our repo, and then deploy it. It deploys it in various stages. Like a dev stage where it's the uptime is not, that goes up and down frequently. And you have sort of a staging system that's supposed to be code that goes there should be able to go to production very easily, and we run various acceptance tests against it. And we have a couple different flavors of services, basically. Some that run Docker containers inside Elastic Beanstalk, and then some that run in Kubernetes. And our CI system, handles both of those things. It auto deploys to those areas.
Also, when we run the tests, our build system, which is Bamboo Elastic's hosted service, we're capturing all of the output from the unit tests or the acceptance tests into one of those JUnit XML format things, and then it shows up in our CI dashboard. And, we can say that the test blah 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 failed, and get a stack trace and so on.
Great.
Yeah. Does that answer your question?
Yeah, that's great. Thank you.
Any other questions? No? Okay. All right.
Yeah, so we're happy to talk to people afterwards if you have wanted to talk one-on-one. So.
Yeah, so next up is a break. Thank you guys. All right, so next up we're going to have a break, about 15 minutes, and just get some more beer. There's a lot of Coors left, and then there's a little bit of other stuff left. So get ready to get your Coors on. But I'll put out a 2-minute warning when we're ready to go. If you are new to the meetup, you should talk to new people. If you don't know new people, just come talk to me. I'm new enough. Thank you. Everyone's sitting down? Cool. So, before we get started, I have a quick announcement from Miles. He runs our weekly programming nights. In case you didn't know, we have a programming night every week on Thursdays. It was at some code school. I want to say it was Code Fellows, but I don't even know. I'll let Miles talk about it. He knows what's up. Miles?
Hey everybody, how are you doing tonight? So it was said that I organize programming nights. That's actually not true. We have a team of 4 people who organize programming nights. Jonathan, myself, Sage, and Paul. Why do we have 4 people? Thank you.
Sorry.
Why do we have 4 people organizing programming nights? This is actually a weekly event, so we rotate hosting responsibilities. We usually have about 25 people showing up. What do you do at programming night? Pretty much whatever you want. If you've got a project that you're working on, you want to show it off, get feedback, you can do that. If you want to give a lightning talk, you can do that. If you want to learn Python for the first time and get your questions answered, you can do that. So it's basically just an informal hack night for Python programmers and aspiring Python programmers. Hope to see some of you there. The new location is at Galvanize, first in Jackson and Pioneer Square. Has anyone been to Galvanize before? What do you think? It's a fantastic space, right? We're really excited. I happen to be in the data science program at Galvanize, so I'm there anyway, which makes me even more excited that we're meeting there tomorrow. But please, if you're at all interested in programming night, feel free to ask any of us questions or just show up tomorrow night, 7 o'clock, Galvanize, first in Jackson. Woo!
Yeah! All right. So now we have our last talk of the night. It's from Dusty Phillips. All of you should know Dusty Phillips. If you don't, I guess the first timers you might not know him. But Dusty is one of the OG founders of PuPPy. So he's the reason we're here today, or at least one of the reasons we're here today. The other one's Don, and the other one's Yannick. Yannick's probably in San Francisco or wherever that guy is. I have no clue, but he's more important than me, so that's okay. Dusty is an author. He's the author of Python 3 Object-Oriented Programming, and he works at Facebook as a software engineer. His talk today is on concurrency in Python, best practices. It's going to be interesting, I'm sure. Dusty, are you ready? Yeah. Let's do it. Woo! All right, Dusty.
So if I stand here, can you hear me?
Yeah.
Closer.
Closer?
It's your fault, Al.
I told you.
How's that? Sweet. You can shout at me later. So yeah, I want to talk about concurrency and parallelism. Probably get right into it because I think I want this to be 40-minute talk, but every time I practice it, it's been about 60. Luckily, I talk fast when I'm nervous. So I want to start with a few definitions for kind of the beginners in the audience. This is going to start out pretty simple and get to the point where I'm really confused, so hopefully somebody else will understand and explain it. So the first definition is concurrency, which is the art of doing multiple things at the same time. And think like walking and chewing gum at the same time. Some people can do it. There are basically, at least in the computing world, 2 kinds of concurrency, at least 2 I can think of. The first is parallelism, which is an easy one to grasp. It's actually doing multiple things at the same time. So again, think walking and chewing gum. Most people can do it really without thinking. And the second kind is actually kind of more standard in computer science world from way back, the 60s, 70s. It's called time divisional multiplexing. And it is the art of switching between things really, really fast. Because I'm executing about 2 billion instructions per second on this computer, really fast means really, really fast. So you can think, back when I was a kid, I had a Pentium 233 single core computer, and it could only execute 1 instruction at a time, because there's only 1 core. So I could have it execute the process of putting a little bit of audio in a buffer and play some music, and at the same time I could make it look like I was editing a Word document. But the computer was actually buffering up the audio, and then while the audio was playing, it would start to read the keyboard, display stuff on the screen, and then it would say, oh, I'm almost out of audio in the buffer, so then it starts putting there, switching back and forth quickly. A more physical example, if you prefer walking and chewing gum as an example, try rubbing your belly and patting your head. I don't know, some people can do it. When I try and do it, I actually have to switch between my head, my mental thoughts are going, okay, pat, circle, pat, circle, pat, circle. That's the closest I could come up with in the real world.
So I want to talk briefly about the difference between IO-bound and CPU-bound problems. This has very little to do with concurrency. An IO-bound problem is one that is spending most of the time doing some input or some output or both, whether it's sending something over network, writing to the hard drive, even displaying something on the screen, although that happens pretty quickly these days. Versus doing heavy-duty computation that is almost exclusively on the CPU. It's just the CPU talking to memory, back to the CPU, and dealing mostly with the registers in the CPU. This is really, really important to classify when you're doing Python concurrency for a variety of reasons that we'll get into. And it's also sometimes tricky. I want to give an example of this from my job. We use SQL Alchemy to connect to a database over the network, do some queries, and the request comes back. That sounds like an IO-bound problem. Most of the time, it's just waiting for the SQL server to do its query and come back. But it turns out when SQL Alchemy gets its result and tries to turn it into an object, that is a CPU-bound problem. The processing the rows and creating an object from it and instrumenting the object so that it can do all the magic that SQL Alchemy does takes a lot of CPU instructions. And so that problem turned out to be CPU-bound rather than IO-bound. I didn't know. So definitely think about that. And this is the last slide that doesn't have any code on it, if I remember correctly. Larry Hastings gave a great talk on the global interpreter lock for those of you who were coming to PuPPy over a year ago. It basically restricts us to using only one CPU in the Python interpreter. So even though almost everything Larry Hastings said, including eyeglasses, has dual core these days, your processor, your Python program, is running on only one of them, even when you're trying to switch between things. That's not actually a problem for I/O if you're waiting on a network call or a disk read or something, because Python actually releases this lock while it's doing I/O, so it can go and do other computation or queue up other I/O at the same time. But what it does is it turns all CPU-bound work into a time-divisional multiplex problem, so you're only using one CPU at a time. It's not parallel, as you would expect, even though your computer has multiple cores. So you have to explicitly be aware of that and work around it as you're doing concurrent development in Python. Oh, there's one more slide real quick. So we'll start with kind of the what I'm going to call the old way. It's definitely not the original way of doing concurrency. And they're called threads. And what you can think of is two separately running instructions in one program. It works for time-divisional multiplexing in Python because of the GIL. In other languages that don't have a global interpreter lock, it will actually allow pure parallelism. And what this does is that multiplexing process of saying, okay, switch to this, switch to this, switch to this, is sent to the operating system. So this computer's running Linux. I can say, okay, here's one thread of Python instructions, here's another thread of Python instructions. Go switch between them at your leisure. Code, sweet. So I'm going to go through my code examples for some of them quite in depth. So I've developed a function called print sleep here. That's just to save room on the next slide. It prints a string and then it sleeps for a little while. And if you ever read documentation on concurrency, you'll find that the time.sleep call is described as simulating work. That's not true. It releases the global interpreter lock, so it's actually simulating I/O. If you want to simulate work, you're probably best off going into just a busy while true do nothing loop. Your computer will get hot. So I've got two functions. One prints a character and 5-character string every half second. Another one prints a number every 8/10 of a second. And then the important part here is where I start a thread, I tell it that the letters function is in the target, and then I call start on it. And at that point, that code is running. And at the same time, the main thread is running it starts running the numbers function immediately. So this looks something like that. The output's going to scroll off the slides for the entire presentation, but mostly I just wanted to get a little bit of overview of what it looks like. The problem with threads is, at least in Python, is that they're actually based a long, long time ago on the Java API for threads. It's not a good idea to base your APIs on Java APIs. That's not a good idea. So I have an example here of kind of the Java way, or another way of using threads. We have a run method that we override. So the default implementation of the thread class is to call the target that you passed into the function in the run method. but you can override it and do some stuff. So in this case, I'm running the method and I'm incrementing this count variable. And then in the main thread, I start the thread down here, and then I change that count variable at a later date. This actually works, but it's not a good idea for a couple of reasons. The first is this count. This is not just a bad idea, but simply wrong. If you're incrementing a variable in two threads, in one thread, what actually happens is your CPU reads the variable from memory. And then later it's going to write the variable in memory after it's done the increment. So there's at least 3 CPU instructions. If the operating system decides in the middle of this to switch to a different thread, you might end up reading 2 things from memory, incrementing them once, and then writing it to memory. So you read, increment, write, and you end up writing 1 increment when you meant to write 2. So you have to do a whole bunch of synchronization using locks or semaphores and a bunch of stuff that I'm not going to get into because I think the API is just horrible. And you'll probably end up either deadlocking your code, which means it just stops running because 2 things or more are waiting for each other, or you're going to end up just really slowing it down because 6 things are waiting for one other thing to complete. The other thing that I don't like about this code, it's a little more stylistic, is that when you extend a class, one of the things that you start doing is adding new methods to that class. And the first problem with that is if you're kind of a beginner with threads, the first thing you'll think is, okay, I'm just going to run this method on this class and it's going to run in the other thread. That doesn't happen. The method always runs in whichever thread that you are actually called it from. That in itself is a problem if you get confused, but even if you're like, okay, I know what I'm doing, you're going to define some methods that are supposed to run inside the thread, some methods that are supposed to run from outside the thread and influence the work of the thread. And eventually someone's going to read your code and not be sure which method does what. So you have to have a bunch of extensive documentation and it gets frustrating. So some best practices if you do use threads. First of all, as I just said, don't subclass threads. Do not access shared variables from multiple threads. If you have to share variables through threads, you should probably use a different API. Or you should use a queue. We'll see an example of that later, but it's kind of one way. What happens is you put something into the queue from one thread, you get it out of the queue on the other thread, and you're kind of passing control, so you know that the variable is only being touched at one place. But my best piece of advice is to actually not use threads directly. Let's use a different API. But before we get to that, I'll talk a little bit about multiprocessing, which was designed to get around the GIL problem by creating a thread-like API. So it is actually a very similar API, but behind the scenes, it's actually running your parallel function in a different process, a different copy of the Python interpreter. That means that you absolutely cannot access shared variables. You'll get some incremented in this variable, some incremented in this process, some incremented in this process, and no change. An interesting thing that people aren't really aware of is when you use multiprocessing, you're not magically getting rid of the GIL. You're turning the CPU-bound problem into an IO-bound problem. And the way that happens is after you've forked a separate process, the CPU-bound work is going to happen in that process. But before you can do that work, you have to pass data into that process. And that happens through a pipe, operating system pipe. And the pipe is actually doing I/O. So you're passing it through into the other process, and at that point, the GIL is being released in both processes. These have to have a separate GIL, and the data is going through. So it's not allowing you to do CPU-bound work, it's turning your problem into I/O-bound. Multiprocessing is very similar to threading in terms of the API, that's intentional. So it has the same best practices. If you're doing it, do not have more processes than the number of CPUs. There's absolutely no way to use more operating system power than your computer has. Minimize the amount of data passed between processes. There's 2 reasons for this. The first is that there is actual latency when you're passing bytes between 2 processes. And the second is that converting a Python object into bytes and then back into a Python object takes CPU time. So you can actually turn your CPU-bound problem that got turned into an IO-bound problem back into a CPU-bound problem. Use Python 3.4 or higher because I'll show on my next slide that it's much faster for doing that, what's called pickling operation, converting objects into bytes. And my best piece of advice is don't use multiprocessing. There are better APIs because it's the same API as threads. So let's just take a look here at how to improve the pickling speed. If you're using Python 3.4 or higher, there are different versions of the pickle protocol that have been developed over the course of Python's history. They started with 0. They're now, the default protocol is number 3, but the highest protocol, which was rewritten as a 3.4, is version 4, as you can see from this. Version 4 was specifically written to be faster and create smaller pickles, which means that when you start, if you set it as your default protocol and start using multiprocessing, you will end up with much faster throughput, which means you can pickle bigger objects before your newly I/O bound problem becomes CPU bound again. So now we're going to talk about a completely different API that wraps threading and multiprocessing. So underneath the hood, futures, or promises they're called in some other languages, in Python it's always referred to as futures, allow you to run stuff in another thread and get a promise that the result will come back eventually, and then you can introspect that result to get some information from it. The important thing is when you're using futures, you're not doing a different kind of concurrency. You're still using threads or processes, and you have to be aware of the issues of shared variables or passing variables back and forth between processes and so on. So as an example, I'm going to take the 10 provinces in Canada, partially because I'm Canadian, partially because 10 is less than 50. And I'm going to connect to Wikipedia if the Wi-Fi is working here, otherwise I'm going to crash my Jupyter Notebook. And I'm going to add a little bit of sleeping because the Wi-Fi is probably pretty good here. I'm going to extract the Wikipedia XML from the resulting text, and then I'm going to get the capital using some XPath manipulation using the LXML library. None of that's terribly important. What's important to understand today is how the futures work. So before we get into that, the sequential version, if you were just going to run this in one thread, takes a while. We process one request, we get it back. We process one request, we get it back. When I used to be on dial-up when I was a kid, this is much faster than that. That's the last one. If you don't know Canadian geography, these are listed basically from west to east or left to right if you're reading the map. They're big provinces, except the east ones. So if we want to use futures instead, we can use this thread pool executor class, and we're going to say, okay, spin up 3 workers. And there are different ways to use this API. You'll want to read up on more of them if you think futures are a good idea. And we're going to call that getCapital function. We're going to pass in a list of provinces, and then we just print out the results as they come in. So the futures API takes care of passing things around. You'll notice it's faster because it's able to do 3 things in parallel at a time. I could actually have gone as high as 10 in parallel, it would have been fine. This was more fun to watch. And just for comparison, we'll take a look at how you would do this using threads instead of futures. Because as you saw, we have 2 lines to do it sequentially, 4 lines to do it using futures, and I can't remember if it's going to be 2 or 3 slides to do it using threads. So in this example, we'll have 2 queues. One takes all of the provinces in, one puts all of the capital provinces out. And then we have this process province function that's going to be running in separate threads. It's going to read a province from the in queue, it's going to connect to Wikipedia inside the getCapital function, and it's going to write the result to an out queue. When the queue is finally empty, it's going to quit. So that's the first slide. In the second slide, we're actually going to do the work of setting up the boilerplate for that. So first we put the 10 provinces on the in queue, then we fire up 3 separate threads. They're going to run that process province function on the previous slide, and then we're going to read the results. And it's about the same speed. It's doing the same thing under the hood. If anyone knows concurrency, they probably got a little bit freaked out. I was freaked out here because if there's some error handling that's missing on the slide, I would have needed at least another slide to get it right. And if it hadn't worked, I would have to restart the Jupyter Notebook again. This is going to be a running theme, by the way. So the point is, there's a lot that can go wrong if you're using threads. If you're using futures, there's less that can go wrong. So I'm not going to give an example of multiprocessing futures, but it's exactly the same thing. It's actually hard to come up with concurrent CPU-bound problems that are not extremely boring, such as calculating primes. So some best practices, if you're using futures, is to make sure that you're designing functions that are going to be run in a future and that those functions take arguments and return values without side effects. Do not access other variables because you are still going to suffer from the same multi-threading issue of two processes accessing a variable. Do not append to a list or change things. Make it a true function in the Haskell or mathematics sense of the word that takes arguments, returns value inside the function. It does work. You can call other functions if you want, but make sure none of them have side effects. If you're using process pool executor to do concurrent CPU-bound work, make sure you have the pickle highest protocol set. And honestly, maybe don't use futures. So, futures are great if you're doing something like this example where you start up the program, you do a bunch of work in parallel, and it's finished. The problem is that a lot of concurrent work is actually more of a thing where you say, okay, go do some work in parallel, and as that stuff finishes, fire off some other work in parallel, and then as that finishes, start fire off some other work in parallel. And in order to work with that, with futures, you have to do something called an event loop, where you basically have a queue of futures that are ready to run, a queue of futures that are currently ready, and a queue of futures that you can actually process results on. And you're bouncing back and forth between this all the time. It's really hard to write or to get right. The good news, it's already been done. If you've been following Python 3 at all for the last 2 years, you probably know it was coming. Async I/O is apparently the new hotness. It's kind of interesting. It does not technically use either threads or processes, although it can, and we'll get into that. One of the things that's interesting about async I/O is that instead of handing the work off to the operating system saying, okay, go switch between this stuff for me, Python does that for you. So you tell Python, that's Python event loop, okay, go do this, and then when that's done, switch to this, switch to this, switch to this. And you don't have to tell it what to switch to, it will figure that out for itself, but you tell it when you're ready to switch. This gives you a little bit of freedom to access shared variables. Still not a good idea, but you know that your function is the only one that's running at the time that it's running, so you don't have to worry quite as much about that. Since Python 3.5, async I/O is a lot easier to write with. Lucas Schlenga, one of the Corsi Python developers, gave a talk 7 or 8 months ago on async I/O. It was kind of hard to read. It's a little easier now, and I've taken the luxury of upgrading to Python 3.5, so the slides look a little better than his did. So we're going to solve. I love Lucas. I work with him all the time. I had to rewrite the requests.get function in async I/O, and the reason for that is when you're working with the async I/O event loop, the most horrible, atrocious thing that will get you shot that you could possibly do is to block the event loop, which is to say, do some I/O and just wait for it, because now nothing else can do any work. Unfortunately, when requests is doing work, it is blocking the event loop. It goes out, it waits for a result, and then it returns that result. You have to do something that's more in the future sense, where it says go out and do a result, and while it's happening, let the event loop do some other stuff. So I used a AIO HTTP library that has been implemented to do this stuff asynchronously, and I created this function. Even worse, I had to rewrite my getCapital function. So it's the exact same function except for these 2 await keywords, which say, okay, I'm going to stop and wait for some I/O to happen. Go on Python, go do some other stuff while I'm working. And we have to wait, and then we wait again on the async I/O.sleep call, which is again not blocking. Other than that, it works the same. This print capital function, you don't have to worry too much about it. Just I added it to make the output look a little bit more fun on the next slide. There was one more thing I wanted to mention on the slide, but you're just going to have to ask me here. Okay, so this is the part where you actually set up and run the event loop. First thing we do is create a new event loop. I had to do that because I'm reusing event loops, so actually in normal async I/O development, you can just call get event loop. I create a new future whose job, async I/O.wait, basically creates futures from iterables. So I'm going to pass in an iterable of 10 futures, one for each province, and then it's going to say, okay, go run those things in parallel, and when all 10 are done, come back. That's why I had to create the printing output loop so we can see that as it came in. So I've been calling these futures. If they're using the async and await keywords, they're actually coroutines. I'm not going to go into the details of how those work, but the magic is you can use async and await on them and get all of this stuff for free with the event loop. So we have this future that actually is a composition of 10 other futures. We're going to run it, and then we're going to close. And you'll notice notice that it's pretty quick. The reason it's quick is not because async IO is inherently better than threads. It's because async IO just ran 10 requests in parallel instead of batching it up into processes of 3. However, async IO is inherently better than threads because each thread takes a little bit more memory than a coroutine, and if you spin up 100 or 1,000 threads, things are going to get kind of messy. If you spin up 100 or 10,000 coroutines, you'll be all right. However, async IO, we just created a client, but it's often used as a server. That's kind of what it's made for. It's used for network IO asynchronously. So let's create a new server. This one's going to take a few slides. So I'm going to take the famous XKCD, if you just bear with me for a moment. We start with this handle capital function, which is going to accept a reader and a writer. That's going to be given to us by async IO, which is listening on a socket as soon as it gets a connection from the socket. It gives us a reader and a writer. It's going to wait for a few bytes to come in, which represent the capital, converts them from bytes to a string. Then it's going to call the previous AL get capital with that promise, and it's going to get the capital back. It converts the capital back to bytes and writes it out, and then it drains the writer. So what this is doing, when you write something, all it does is throw it on the buffer of the writer. But when you call drain, it actually says, okay, wait for that to happen. Let the event do some stuff. And then we clean up after ourselves when it's done. Now, before we actually write the server, let's take a look at what the client for this will look like. So we open a connection to localhost on a very modern port. We write the province out to it. We read the response, get the capital from the response. So this is coming from the server, not from Wikipedia, and then we return it. And we have the similar print capital as before that outputs it. So the important thing to kind of, well, maybe it's not important, but something that you may have missed on this is that I've created a new protocol. The protocol is, it's kind of like NTP. It says receive a connection, read a province, return the capital, and close the connection. That's one protocol. It could be saying, okay, wait for HTTP. It could be doing anything else if you wanted to work with different streams. Now things are going to get a little freaky because I'm going to run the server and the client in the same event loop. Let's do that first. See how it goes. Yeah, it didn't crash. So what just happened was my client, actually 10 clients, sorry, no, that's not true. One client connected to the server, it sent the province to the server then connected to Wikipedia, got the capital back, returned the capital to the client, and then the client printed it on the screen. That happened 10 separate times. So it's a bit of a weird network flow. It all happened in one event loop, but it's important to understand that this happened over the TCP networking stack, and the server and client could easily have been on opposite sides of the world. It would have been a little slower. So the word async IO makes you think it's only about asynchronous code, so using async and await, and then it's only about IO. This isn't true. Async IO can do event loop style stuff with futures. It can put stuff in other threads, and it can put stuff in other processes and get the result back. And so to illustrate both of these features, I decided to come up with a CPU-bound problem, encoding plain text into a compressed system using the Huffman encoding scheme. This is the most interesting set of slides that I have, and I'm just going to skip right over them because they have nothing to do with concurrency. If you want to know more about Huffman encoding, ask me afterwards. Yeah, this one just didn't work too. Yes. So, my example, using async IO as a server, this time it's going to connect to Project Gutenberg, it's going to download a random book, and it's going to compress it. See how it does. First I'm going to make a process pool executor. This is the same thing as the thread pool executor that we saw before. Exact same API, it's not a special one for async IO. And it's just going to run some stuff, the compression itself in a separate process. I'm going to get a random ID. We're going to connect to the Project Gutenberg mirror and download that ID. I checked the Gutenberg front page before I started doing this, and I'm really glad I did because apparently they shut you down if you try and automatically request stuff from their site. Connect to the mirror. You get the bytes from, or first you get the string from that URL, and you convert it to bytes using the encode method. And then this is where you do the parallel work. You call run an executor with this pool that we have up here. You call the huff and code function that I glossed over on the previous slide, and you pass the bytes into it. Output some interesting statistics, and then we call loop.runInExecutor again, this time with no, not passing in any thread or any executor. That means it's going to use async.io's default thread pool executor. We're going to run the write file function, and we're going to give it a function in the encoded bytes. So this is happening in a different thread, and you might be wondering why I'm doing it in a different thread. Async.io does not have a good method for calling I/O to disk. This is partially because disks are fast enough that maybe it doesn't block the event loop. And it's mostly because operating systems make that really difficult, especially if you want to support all of them. So in order to get around that and keep my code all nice and non-rocking, I just wrote the file in a separate thread. It's not talking to any other functions or anything, not connected to any variables, so it's not going to hurt anything. So we're running synchronous code, the write file function, using async.io, and we're running CPU-bound code, the Huffman encoding function, using async.io. Async.io, maybe not such a good name. And just to see how this looks, this one could take a while depending on which random books we download. Oh, no, it's not too bad. So these two that are 1,768, they're actually 404 errors because my random selection algorithm is a little bit shaky. It's doing the exact same thing as the previous client, so the important part was seeing that you can run it in an executor. So let's talk about some best practices with async.io. Number one, first and foremost, use Python 3.5. Woo! Or 6. The async and await keywords make your code so much easier to read, and it's just easier to reason about, easier to think about. Just start writing it using 3.5 immediately. If you're having trouble getting 3.5 installed for some reason on your operating system, use Anaconda. It will work. It's what I use to get it running here. And it doesn't matter what else you're using. So if you were writing previously some code to loop over futures and it's getting complicated, stop right now, use async.io. It's a well-tested production event loop. It was written by Guido van Rossum. We like to think he knows what he's doing. You don't have to use async and await, as we just saw. You can use futures. So you can start using it immediately with your synchronous code. You do not have to wait and start rewriting everything to use the async keywords. And you can even start doing that later. But maybe you shouldn't use async.io. Anyone noticed any themes here? So this is a really neat library that Dave Beasley. Who here knows who Dave Beasley is? Woo! Oh wow, you guys are missing out. Go home tonight before you go to bed. Watch any Dave Beasley talk that you can find from Python.
You won't sleep for days.
You won't sleep for days, and your head will explode. But he'll be very polite about it. He will tell you that he's going to explode your head. So one day he got bored and decided it was time to write some more concurrent code. I've seen this guy write live code with no syntax highlighting in Emacs in front of about 200-300 people. He didn't make very many mistakes. It was shocking. So to demonstrate Curio, which is basically, it does the same thing as async.io. It provides an event loop, or at least you can think of it as providing an event loop. It actually simulates a kernel operating system CPU schedule. But we're going to decode the files that we created in the last example. It's really a very similar API to async.io, but much easier to read, in my opinion. And I find that kind of depressing because Guido wrote the async.io library, and he also wrote Python, and Python is the best coding API in the world, and async.io is not quite the best because Dave Beasley trumped it. It's also somewhat faster than async.io. Sorry, I don't tell you why I gloss over the slides for the same reason as before. Decoding Huffman encoded compressed trees is kind of tricky. So we're going to have 3 async and await functions here, coroutines. This is easier to read from the bottom. We're going to loop over the, excuse me, just one second. That should sound better. We're going to loop over the 10 files that we saved in the previous example. We're going to create a new task on Curio that says go run this thing in parallel, and that task is going to call print decoded. Print decoded is just something that will print something as soon as it gets an output. Print decoded is going to call the decode file, which is up here, and then output the data. So it's kind of just a visualization example. decode file is the important one. It's going to open the file. It's going to call curio.io.stream, which is Dave's way of doing file I/O asynchronously. I didn't test it on Windows, it might not work there, but it was working fine in my examples. I'm going to read from the stream, and I'm going to wait there, so it's actually doing an async call. Then I'm going to wait again while I call run in CPU bound, which is so much easier to remember and understand than run an executor process pool. I'm going to pass in the huff decode function from the last slide, and I'm going to pass the bytes into that function. So that's going to be happening in parallel. And then to turn it all on, we call curio.getKernel. We add the task for decoding the 10 separate files, and then we run it, which again looks a lot easier to read than async I/O, in my opinion. And the first one was a 404, but we've seen the stuff's being decoded. If you've ever used BZ2 or BZ2 to decode files, you'll notice it's really slow on the decoding. It's the same algorithm, only better. So it took a while. We have some Shakespeare in here. I've seen some really weird stuff as I've been testing this, most things I don't recognize. So Shakespeare and missing stuff, that's an interesting one. So briefly, best practices for Curio. You must use Python 3.5. Curio itself uses the await and async keywords. Apparently, Dave Beasley just wrote it because he wanted to experiment with those keywords. He's been kind of building this run example for years. Every PyCon or conference he attends, he does another talk that's kind of based on this. If you're going to use it compared to async I/O, it is faster and more readable. It's got this really neat debugging monitor that kind of allows you to see in semi-real time when tasks are running and how long they took and things like that. And of course, you might have guessed this one, maybe don't use Curio. And the truth is, I don't have anything better. We're approaching the end of the talk. But Curio is a really fun little library written by a very smart man, the same man who wrote Squiddy. He's a shame. I really like it. I really like the API. Like I say, it's faster and more readable. It's been benchmarked against Twisted to be faster than that. But it's not the one that's got community momentum. It's not the same API as async I/O, so you can't drop and replace your application. You can't say, okay, I'm switching from async I/O to Curio magically. You have to actually change your code to some extent. Coroutines themselves probably don't need to be changed, but the boilerplate where you're starting the event loop and stuff do need to be changed. And my experience through my years of software engineering I like to always use the best or most interesting or fanciest library, and I always get burned. It's generally a good idea to use the most popular library. And the reason is, even if it's inferior, it will get better faster. Any good ideas that exist in another API will be ported over. This is why I generally recommend Django, even though Alan will insist on Flask. He's not shouting now.
Woo! How about that?
So, as a kind of summary for concurrency, use Python 3.5 or newer. Just use the latest version, in spite of everything I just said about not using the latest version.
Woo!
Python is the most supported. Can somebody hit him on the head? Python 3.5 is the most community supported version at this point. Nobody's developing older versions of Python, so use it. Make sure you classify your problem as I/O or CPU bound, and make your decisions based on that. You'll have to test a little bit to make sure that you're doing the right thing, because as I gave the example earlier, you may not always be right if you just guess. It's the same as any optimization. You can use threads or multiprocesses if you just want to spin up separate tasks that don't communicate with each other. I use threads often if I need to just spin up a signal handler that's going to kill my main thread if a signal happens, something like that. If you're doing one-off parallel tasks that you just want to do a bunch of stuff and then you're done, features are a great API. And if you're starting to get a little bit more complicated, you need to do some event loops, use async or Curio. Choose the one that you like the best. And if at all possible, don't do concurrency. If you haven't figured it out, it's really complicated. These APIs have been developed over the course of years, decades. Once upon a time when I was first learning concurrency, trying to learn concurrency, I don't think I did well in that class, threads were the way to go. They were considered the easiest way to understand this stuff. Coroutines were those things that Donald Knuth developed in the 70s and nobody who understood anything would ever use. Coroutines are now considered kind of the way to go for this specific problem. I have played with coroutines in a few different contexts, and except for once, every time I do it, I finish the coroutine-based example, and I'm really proud of myself because I did this complicated thing. And then I look at the example and I'm like, well, that could be simpler, and that could be simpler, and I pull it apart, and all of a sudden, I'm just using a generator. I'm like, you know what? That could be simpler. And then it's just a function call, and all my coroutine boilerplate was wasted. But they're fun to work with. They're fun to play with, not work with. They're mostly good for the buffering problem, which is what all I/O is. We don't think about buffering much in modern systems because they've all been abstracted away in the libraries or even the operating system. But Donald Knuth thought about them a lot. He thought about a lot of things. Just briefly, this is the list of things that I wasn't importing on the slides, so the slides will leave more room for output. The top ones here are all standard library modules, if you use Python 3.5 anyway. Async.io, I don't think I actually used counters, that came from that later. The executors come from concurrent.futures. I use pathlib to process the Huffman path. Q for that Q example, random because I was sleeping or something. Threading for threads, and time for time.sleep in asynchronous code. I had to install some third-party libraries. AIO HTTP is kind of the de facto standard way of doing HTTP using async.io. It's not a web framework. It is an HTTP library. It provides all the protocol level support. There are web frameworks built on top of it. The bit array library was used in the Huffman encoding example for converting bytes into bits and doing a bunch of manipulation at the bit level. You didn't have to see that. If you want to, we can look at it. Curio was, of course, Curio. I had to install the master version instead of the version that's on PuPPy. I had to do that because it wasn't integrated properly with the Jupyter Notebook. There was something that wasn't closing properly, so that works. I used LXML to get the etree stuff, and I used requests for the same reason everybody uses requests. That's pretty much all I have. Alan mentioned my second copy of my first book up front. It contains a chapter on concurrency. You might wonder why, because it's not exactly an object-oriented topic. The truth is it was because I wanted to write a chapter about concurrency. It goes into a lot more detail about a lot of these things, but it's sadly out of date. This was published in August. Python 3.5 came out in September, so it's using coroutine and yield from instead of async and await, so it's a little harder to read. That makes me sad. But it's a lot of fun, and if you want to read the rest of the book, you'll actually learn a little bit about object-oriented programming. But I'll tell you a secret. Most of the book is about not using object-oriented programming. Python is probably the most object-oriented language in the world, but it hides all of those abstractions away underneath really beautiful syntax. So when you're using a list, you don't think of it as an object. When you're using a generator, you don't think of it as an object. When you're using a coroutine, you don't think of it as an object. Functions, objects. Classes are objects. Types are objects. So most of this is, well, this is how you would do it if you wanted to do object-oriented programming, but if you wanted to do it the Pythonic way, this is how you would do it. So read the book even if you're not interested in object-oriented programming, and give it good reviews on Amazon. So I've got some other stuff up here for you to read or write down while I take questions, if there are any questions.
If you have questions, raise your hand. Echo? Oh. You're closer, Brett. I'm gonna get you.
Faster, Alan.
Oh, quick, Brett, make it quick.
Dude, I can run over there and back here. And
come on. You have longer legs. That's not fair.
So you're essentially conceding to the Scala and actors and messaging as far as in concurrent testing environments or something? I mean, the Scala guys would love to hear that.
I think so, yes.
Ooh.
You should not do that.
All right, other questions? Oh, all right, I'm going. Is this faster for you? Is this good?
I just want to see you run.
Oh, okay.
I'm just curious. I'm curious about debugging async IO.
Yeah, everybody is.
Thanks, Dusty.
There's async.io itself has some really nice environment variables that you can set that will output some stuff when you run it that basically says when coverages or anything. It will output a bunch of warnings at the end saying you did something wrong if you did something wrong, but it won't tell you what. At least until you decipher them, which I don't think I have. There's also one benefit, which is if you are not using futures in some way, you know that your code is running in one place at one time. You can, when you see the stack trace, you know exactly what function is running. You don't have to worry about interaction effects with other threads. So that means that you have a little bit more freedom to use something like PuPPy immediately in that location without other threads interfering with your IO.
Other questions? Raise your hands, please. Oh my God. All right, Dust. Oh yeah. All right, good.
If there's no questions, that mean that I did.
Oh no, I've got one for you.
Like things like twisted and g-event, like try and do this without any changes in syntax. So is it absolutely necessary, do you think, to change the syntax to do this?
Absolutely not. Twisted's been around for longer than I've been using Python. The syntax was changed to give you a much more sequential reading of your code. If you've done much Node.js programming, and I hope you haven't, you have to do all this callback stuff, and that's the same thing in Twisted. I haven't used gevent, but I understand that it's a little bit less so. Same with stackless. You end up having to split up your logic, like your psychological logic. You say, okay, I have to do a little bit here, and then when that's done, I'm going to do a little bit over here. So the syntax makes it easier to read and write, maybe not debug, but it's definitely not necessary. And in fact, you can use, I can't remember the name of the library off the top of my head. There's a backport, no, not turning out. There's a backport of async.io to Python 2 that does not use the async in a way or even the yield from syntax. It's not available. It's wrapping stuff in futures dynamically, as I understand it. I've never actually used it, but it does not require the syntax changes.
But also maybe just use Python 3.
0.5.
Yes. Questions? None. None. Dusty, we've got a little bit of time. I have a favor.
I have a question, actually.
Oh, great. What's your question?
So, Flask.
Oh, you're going to grill me on Flask? Here's the deal. The talk I gave was on bottle. I never gave a talk on Flask. I'm often confused with some Flask lover. I've written like 5 lines of Flask. I'm a bottle guy.
Yeah, but they were good lines.
They're probably good lines. No. Yeah, if you...
They're the same API, come on.
If you don't need it, don't use it. Right tool, right job. And often I think Django is just much overkill. Question to you, buddy. You're a big Python 3 advocate, obviously. You gave some good examples today. But could you give us a couple other reasons why maybe Python 3 is better than 2.7.11 or whatever else you may be using? 2.7 whatever, or 2.4, because why? I don't know. People do it. Whatever. Python 3 why?
What do you use at work?
Nothing.
Alan?
Nothing.
I use Python 3.5 at work.
Shut up!
And I love my job. Oh, we're hiring.
Where do you work?
Facebook. We're always hiring.
Oh. Got that stock money.
The benefits of 3.5 actually follow Planet Python. There were 2 blog posts, both written by Microsoft developers in the last 3 days about why you should use Python 3, I think. Number 1, as a 3.5, it is generally faster. I think Brett Cannon's talk was about that a few months ago. Number 2, it's much, much more pleasant to read. I'm going to tell you a little secret. Python 2 is my 3rd favorite language in the world. It's outdated and it's kind of clunky, and when I go back to read and write it, I feel a little bit angry. I get angry very easily when I'm writing ugly code. I get very angry when I read and write JavaScript. But my 2nd favorite language in the world is ECMAScript 6. It's they borrowed all of the best ideas from Python. They took away most of the worst ideas from JavaScript 5. And it's a nice language. Python 3 is better, but ECMAScript 6 is better than Python 2. So if you're using Python 2, it might be time to switch to Node. The blog post that I read yesterday from the Microsoft guys was saying that as of maybe May, if you do some fancy data science on the PuPPy index, you will see that Python 3 is actually better supported. There are more actively developed libraries that are supporting Python 3 or Python 2+3 than there are that are supporting Python 2 or 2+3 in total. The graph goes like this, and they figure if they project it in May, that will, Python 3 will actually be kind of de facto standard. It'll take a while for people to realize that, but the truth is your dependencies probably are ported. I've lost track of how many counts, so number 18. It's actually a lot easier to port your app to Python 3 than you think. Brett's done a ton of work to make it, to make it easier. He's got a whole bunch of documentation, I think mostly on the Python docs, but also spread throughout his blog and stuff. If I remember correctly, it's snarky.ca. Really
Yes.
I got that one. So jealous. So it's really generally not that hard. The one time that you will probably have a lot of frustrating manual work to do is if your code does a whole bunch of manipulation of bytes and strings and you did it wrong. And if you did it wrong, there are bugs in your code, so you should probably port it to Python 3 to fix it. If you are doing a lot of byte manipulation in your code, you're probably not writing end-user libraries. You're probably writing a protocol off thrift, HTTP, something like that. In which case, people depend on your library and you should port it. I heard that even the vocal anti-Python 3 Mercurial guys are talking about porting it in the next couple of years. It's time. It was time last year. Now it's past time, so do it.
What's your number one language? Because you definitely skipped over that.
Python 3.
Oh, okay. Sorry. Oh, I'm sorry. I just wasn't paying enough attention. I'm an asshole. My bad.
Well, leave that.
You have a question?
No, I just couldn't hear what your second language was.
Oh. ECMAScript.
ActionScript?
ECMAScript. The new version of Java. JavaScript, sorry.
Yeah.
The new version of Java is as bad as the old version of Java.
It's better. It's not bad. It's not great.
The new version of C++ is a lot better than the old version of C++.
I have the version of C# too.
C# been good all along.
Yeah, I know.
I mean, if you aren't going to see anything other than that miss city.
Indeed uses a lot of Java. Maybe we should stop talking.
We're upgrading to 8. It's got lambdas and stuff.
Oh, that's good. That's good. That's good. All right. Dusty, round of applause. Thank you everyone for coming out. This concludes the meetup. There's actually no more beer left, so if you're planning on sticking around, you can't because there's no beer. However, we are going to Fado. If you know where Fado is at, go. If you don't, follow me. I got a hat on, and I'm the guy with the microphone right now. Thank you for coming out.
Every time he says follow him, he doesn't actually know where he's going.
Today, I actually know where I'm going because I go to Fado often enough. I don't know if that's good or bad. Shout out to Indeed for hosting us tonight. Round of applause for Indeed.